Well, hello, J-Chem family. We want to introduce matter. We're finally getting into the basics of chemistry. So let's talk about what is matter made of, how are elements and compounds different from each other, and maybe even discuss why I love the smell of Elmer's glue. Let's get to it, though. No hesitation. Matter. You look around you, anything you see is basically matter. Anything that has mass or volume, meaning for your purposes, you think of mass more like weight, but mass is different than weight, and we'll get into that later in the year. But if it takes up space and has a weight to it, it therefore has to have a mass as well, and therefore it's matter. Solids, liquids, gases, and plasma are all considered matter. So this right here, the air that you breathe or outside any smoke or fog, that's a gas. Sometimes we forget that that is matter as well. If you don't believe it, blow air into a balloon. It takes up volume, right, in space. And if you weighed a balloon with and without air inside of it, the balloon with air in it would actually weigh more. So anything with mass or volume is considered matter. So that just basically leaves light and energy in that as not matter. Otherwise, we really just have everything around us that's matter. Now, atoms are the things that make up matter. They're the smallest little particles of matter that still maintain the object's identity. So gold in a ring, if you did pure gold, an atom of gold would still have all the properties of gold. When you start splitting it apart into its electrons and protons and neutrons, it no longer acts like gold completely. So atom is the smallest piece that actually maintains that object's identity. Now, atoms are so ridiculously small. I think someone told me once that there's about 10,000 little tiny atoms at the very tip of a needle or a pin. Okay, so these are crazy small, and we can't see them with the naked eye. So how on earth do we even know that atoms exist? Well, a scanning tunneling microscope is certainly a big help. It can actually give us a digital image of the little bumps and little individual pieces or particles, or what we call atoms, on the surface of something like a metal or that. Again, we can't see with our naked eye, but all of our study, research, and even our digital images from scanning tunneling microscopes leads us to believe that there are these little building blocks in all matter. Now, matter can be broken up into two things. It's either a pure substance or a mixture. If you are a pure substance, you are either an element or a compound. Now, the important thing about pure substances is that it has its own unique identity. So anything that is a pure substance has its own unique properties and identity. If you get into mixtures, which we will in a little bit, you will see that mixtures don't have a specific unique identity. All right, and we'll get into that as we go. But let's talk about the two branches of pure substances, elements and compounds. All right, so an element is basically a type of matter that's only made up of one kind of atom. So we talked about gold earlier. If it was pure gold, it would only be made of gold atoms. If it was silver that maybe you mined from the ground, it would only be made of silver atoms. Now, elements are found on the periodic table, we know, and they have different names for many different reasons. Some of the times we name elements with Latin words. For example, sodium, which is a very common element we will use often, its symbol is actually Na. And you might think, how on earth did we get Na for sodium? But it's actually originally from a Latin word that was called natrium, and then eventually we led to calling it sodium. So that's why sodium doesn't actually have a symbol with an S in it. It's from a Latin word. Some countries have actually been dedicated in naming elements, such as polonium for Poland. Madame Curie isolated polonium and gave props to her home country. All right. And by the way, Madame Curie is an amazing chemist. Also, one of the first women who actually got real big props for chemistry. As you know, in history, women unfortunately have been overlooked a lot in many different facets. Science is no exception to that rule, unfortunately. So thank goodness we are moving forward. Women need to get just as much props as men, obviously, in the field of science, as well in all fields. Equality all the way on this one, for sure. Now, states, Californium, we have an element named after famous people, Einsteinium. The basic thing is that once you have an element that is actually found, you have the right to name it yourself. So whatever you want to give props to, by all means, go for it. So for element symbols, the only important thing to really know is that they're usually one or two letters. The first letter is always capitalized, and the second letter you must lowercase. For example, sodium we said was Na. You definitely want the N to be capitalized and the A to be lowercase. The reason for that is when we start writing compounds, you want to have capital and lowercase to know when and where there's a new compound, or an element forming. So this would be sodium and Cl would be chlorine. If you put it all together with capital letters like NaCl, it might get very confusing as to what element is what. Are these 4 different elements, 3 different elements? You know what I mean? So it is important to keep with that. All right. This is something that's just interesting. I find it's the top 10 elements on Earth, the abundance of it. Hydrogen is totally number 1, and if you notice, the lighter elements tend to be more prevalent than the heavier ones. But hydrogen, definitely. Majority of stars are made with hydrogen, and majority, and maybe even all stars. That's a great question. I am not a pro with astronomy by any means, but many stars, if not all, are made of hydrogen, and they fuse together and they make helium. So it's not surprised that these stars are churning out helium all the time. Now, oxygen is only 1.1% on Earth, so we really have to take care of our oxygen supply. As humans, we need that to live. All right, but interesting to see, hydrogen is number 1. And again, if we could use hydrogen as a fuel source, that would be amazing, because if you took hydrogen gas and you burn it, which means you react it with oxygen, you end up getting pure water as a byproduct. Pure water as a byproduct seems to me like a way better solution than all the bad things that are being emitted from our gas tanks, our exhaust pipes that are putting greenhouse gases into the environment. Now, the other type of pure substance besides elements are compounds. And compounds basically are just 2 or more elements that are now combined together because of a chemical reaction. So there's a chemical bond that's holding them together. For example, water, H2O. There's 2 hydrogens for every 1 oxygen. That is water. It has its own specific unique properties, and it's set in a fixed proportion, which is why it is considered a pure substance like elements. It has its own unique set of properties. Now, if you want to talk about the smallest unit for a compound, you can often call that a molecule. We'll learn later there's 2 types of compounds. There's molecular compounds and then something called formula units. Formula units will be for our ionic compounds, but again, we will get deeper into that when we talk about bonding. Either way, compounds are held together because of chemical bonds. And the bonds, what you can think of, is like the glue that lets them stick together. Now, we will go into why chemical bonds actually happen and form, but basically things will come together and stay in order to lower their energy. Everything is about trying to lower the energy to make this chaotic world a little more organized and less stressed. But that will be coming up in the months ahead. So what's the difference between an element and a compound? First of all, please remember that an element and a compound are both considered pure substances, which means they have their own unique identity and set of properties. The only difference is a compound could be broken down with chemical reactions into its individual elements. So again, if you have water, which is H2O, and you run it through electrolysis, you can break it down into its oxygen and its hydrogens, right? And technically, oxygen doesn't really go by itself. It likes to pair up with itself, but we'll get into that. That's called a diatomic molecule with the months ahead. We'll talk about that as well. Anyways, compounds can be broken down into individual elements. Now, if you're not a pure substance, right, then you are a mixture. So we had pure substances, right, and we have mixtures, and all of that falls under matter. So matter is either a pure substance or a mixture. We already talked about pure substances. Now it's time to talk about mixtures. A mixture is nothing to do with chemical reactions whatsoever. It's just the physical blending of elements or substances together. All right? So what we're going to do is, if we mix anything up, it's going to keep its own separate properties. So in the example of Chex Mix, if I mix together Chex and pretzels and garlic rounds and all that, even though they're mixed together, they still keep their own specific properties. So the pretzel still tastes like pretzel, the garlic rounds still taste like garlic rounds, etc. So if you recall maybe from back in junior high, elementary school, there are two types of mixtures. There's a heterogeneous mixture, and the prefix hetero stands for different or not uniform. So a heterogeneous mixture would be something like a salad, where it's mixed together but you can see the different pieces. Or even sand and water. You mix them together, but the sand and water, you can still tell the difference between the two. It doesn't look uniform. That's what a heterogeneous mixture is called. Our classroom is often a heterogeneous mixture. It's just a mixture of different people and different things all in the same place. We all maintain our own specific identities, but we are mixed together. The last and final type of mixture is a homogeneous mixture. Now the prefix homo, right, stands for similar or the same. So particles will be uniformly spread out, meaning that they'll be fully dissolved in the mixture, which means that even though it's a mixture, you can't see the individual pieces with your naked eye. So for example, something like Kool-Aid or lemonade, when you mix it with the water, all the little sugar, artificial flavors, and artificial colors are blended so well together that they're uniformly spread out, and you can't tell the difference between them unless you looked under a microscope. That is a homogeneous mixture because, again, you can't see the different pieces. The air that we breathe has way different types of gas in it. There's oxygen, carbon dioxide, methane, some nasty things that we don't even want to think about that we're breathing in. It all looks the same to us, to our naked eye, but it is mixed evenly throughout. And then another one that surprises people sometimes is tap water. Your tap water isn't pure water. It has chlorine in it for disinfectant if it comes from the Chicago municipality. It has fluoride in it in order to help prevent tooth decay, amongst other things as well. If you have well water, you have extra calcium and magnesium. Your water tends to be what we call harder, right? So it looks like water, but it technically is a homogeneous mixture because other things are mixed within. All right, thanks for listening up on matter. Again, two branches of matter are either pure substances or mixtures. If you're a pure substance, you're either an element or a compound. And if you're a mixture, you're either homogeneous or heterogeneous. All matter fits under those categories. Thanks for listening, JChem family, and have a great day.